tell you immediately, today is gonna be a tricky exercise, so take a very long and strong coffee, brace yourself, and we are ready to go. This time we have to create a function that displays the number entered as a parameter. The function has to be able to display all possible values within an int type variable. Here's the prototype. So as usual, we have a function that doesn't return any value, but this time takes an integer as an input. For example, if I call the function putnbr42, it has to display 42. So we have to convert this integer 42 into this char 42, or better, this string 42. Let's dive into the code. This is the program in all its glory. As you can see, it's not that long, and I would argue it's not that complicated, as I said before. The thing is that you need to grasp some theory to understand really what is going on. So very briefly, let's just check these two functions, and then we jump into the theory I'm talking about. Here I have my main function, in which I call many times the function putNumber. I put the integer -42, the integer 0, 42, and then I put this very strange number, which is 2,147,483,647. And basically I put the same opposite number, but in negative, +1. So it's going to be -2,147,483,648. Okay, what the heck am I doing? Let me explain better. These two strange numbers are the maximum value representable into an integer data type. I mean, inside 4 bytes of memory. And this is the minimum value representable into 4 bytes. So at this point, to really understand this concept of maximum value, minimum value of a specific data type, we have unfortunately to cover some theory. But believe me, it's going to be fast and not boring. And I will make as easy to understand that even a little kid can grasp this concept. Okay? Promise. We're going to start our journey with this recurring joke in computer science. Allegedly, this joke states something like, there are 10 types of people in this world, those who know binary and those who don't. This is indeed a very stupid joke, but it has a point. The point is that this 1 and this 0 is just a symbol that represents a value. So the symbol is not the value itself. Let me dig into this rabbit hole a little bit. Once upon a time, we had the problem to represent stuff in a more compact and easy way. If I had 4 ducks, for example, I could have drawn all of them, but as you can easily understand, this will become very soon a very inefficient mode to express some quantities, right? If I wanted to say, for example, I have 4 ducks, I had to draw 4 ducks, which is going to be a long and tedious exercise. Long story short, symbols were required, aka some abstractions that are able to represent some value, okay? The most primitive abstraction that we can come up with is the lines. So we have 4 ducks, it's going to be 4 lines, simple, as easy as that. Even this abstraction, though, is not very efficient. If I have 27 ducks, what do? 27 lines? Are you crazy? It's gonna be tedious again. Therefore, we needed a better abstraction, like the Roman numeral system, which has different symbols for different values. I have symbols that are able to represent bigger quantities. I can therefore represent more things with less symbols. It is already a good abstraction to represent bigger and bigger quantities. So this is the main idea behind abstraction of representation of some value. In the Roman numeral system, to represent 27 ducks, I need only 5 symbols. Meanwhile, in the very primitive lines abstraction, I need 27 of them. So you see that we are finding ways to represent bigger and bigger values through the complexity of the system representation. Key idea here from this slide is that we have many symbols that are able to encode the same value. 27 lines are equal to 5 letters in the Roman numeral system. They encode the same value. So let's get in touch with these symbols that represent a value. If I want to represent the value 5, I mean 5 things of something, I have a plethora of symbols that I can use for this goal. I have, for example, the symbol V in Roman numerals. I have this strange symbol from Babylonian numeral system, which is like 5 goblets, kinda. Then I have the 5 coming from the Chinese numerals, which is very similar to our Indo-Arabic 5, but nonetheless different. Then I have the series of characters that encode the value 5. In this case, I've used the Cyrillic alphabet. That is the number 5 in the Russian language. It is read like yet, and it means 5. So you have a series of characters that together mean a value. A series of characters is indeed a symbol as well. Now, given the arbitrary nature of symbols, we have that the same symbol can mean something different depending on the context, right? During the war, Churchill used to make this symbol that stands for victory. It doesn't mean like 5 in Roman numerals, or 2 like 2 elements, or a strange arrow that points toward the bottom. In that specific context, the symbol V meant victory. It was the V for victory. So here I say the punchline that I hope you won't forget. The value of a symbol is in the eye of the beholder. So the value of a specific code is context dependent. Let me give you another example. The word gift. If you decide to read this word in German, it means poison, which is a very different decoding of the word gift in English. So the same symbols, as in this case, a series of characters, can have very different meanings depending on the context. Nowadays, to represent numbers, we use the Indo-Arabic system, which until now has proved to be a very efficient system. As you know, we use these 10 drawings, which are not totally arbitrary because every single drawing has the same number of angles as the value it carries. The concept is the same of the Babylonian numerals as well as the Roman numerals. We have a series of symbols that encode a specific value. In our system, we have 10 symbols. That's why we talk about base 10. In Babylonian system, we have base 60 because there are 60 sketches that represent a value. Indeed, you should further your interest in Babylonian system because that's why we have 60 seconds in a minute. And this is going to help you to better grasp the concept of a base. Now a question, why we use a base 10 system? Why the heck we need 10 symbols, 10 sketches, 10 patterns to represent a value? Well, very simply because we have 10 fingers. That's all it is. So we needed 10 sketches that represented the value of the fingers we were using to count. That's it. So 3 fingers are represented by the symbol 3, which has 3 angles. So the sketch for the number 3, the pattern for the number 3, is an abstraction for the number of fingers. Okay? So in our human base 10 system, to represent 10 ducks, how do I do? Well, I have 10 symbols that range from 0 to 9. So I don't have a symbol for the number 10. You know that our Indo-Arabic system is a positional system. It means that when I fill one level, I just add 1 to the upper level and 0 the current level. That's how positional numbers work. So when I arrive to 9, I have filled my slot. I've ended my symbols available in my specific base. So what do? I add 1 to the bigger slot and 0 my current slot. So I can keep going on counting. That's very easy, and we all know this. So the number 10, or better, the symbol 1, 0, in a base 10 system, in our system, means 10 elements. Why? Because we have 10 fingers. Pay attention here. If we had less fingers, like, for example, Mickey Mouse, who only has 8 fingers, first of all, we wouldn't need the symbols for 8 and 9, right? Because I don't have enough fingers. I don't need the number 8 and the number 9 because I miss these fingers. What the heck should I represent? Something that doesn't exist? You get the point, I hope. So if we were, all of us, Mickey Mouses around the world, we would have developed symbols to represent values until 7. From 0 to 7, 8 symbols. So we would count 1, 2, 3, 4, 5, 6, 7. Here comes my last finger. What do? I do the same as in our base 10. I zero this and I raise in the upper position to 1. But here's the catch. Now, the number 10, namely the symbol 1, 0, what is the value it carries out? You got the point, right? Now the value is 8. 8 ducks in our base 8 system. Okay? Are you getting it? Pause. Maybe just take your time to digest this concept. I think it's trivial, but at the same time, it's a fundamental concept. Understand numbers. Let's go on. Now we get to our binary system. Let's pretend we have 2 fingers, or better, 2 fins, like a dolphin. You have only 2 flippers that we can use to count stuff. So I don't have anymore any 10 fingers or 8 fingers. I need another base system. My base system, of course, is a binary system because I have 2 symbols. I have a 0 and a 1, for example. And then I say, I have to count 2 ducks. I am a dolphin now. I say, okay, I have 1 duck, and then I have another duck. So what do? I filled my level. I don't have any more symbols. I 0. I raise to 1, the upper level, and then I 0 my current level. Which is the number I get? Yeah, of course, it's the number 1, 0. It is not a 10. It is the symbol 1, 0 that encodes, that carries out the value 2. 1, 0 in this case for a dolphin is 2 ducks. If you understood this, that's done. You understood how binary numbers work on a deep level, in the marrow of your bones. There are 2 types of people in this world. Dolphins, get it, with no explanation, and others, okay? I hope this is a punchline that you will remember forever. Because, you know, our mind is kind of tricky. It only remembers stuff that is outside the box. So all the punchlines which are not usual for you, they will stick to your mind. Now we are ready to tackle the concept of overflow, which is what we need in our exercise. Think about your car and your odometer, the thing that counts the kilometers that your car has done. And pretend that our odometer is at the maximum state, so 99999. This is an odometer with 6 digits. What is going to happen if I add 1 to this odometer? Well, of course, we're going to start again from 0. So the car is brand new. Hurrah! Nice. Now, the concept here is that we have a fixed amount of digits. An odometer is a mechanical stuff. There is not a 7th digit in which the 1 can go and make the number a real number. When we add 1 to this odometer, mechanically we go to 0 again. You know, we can do the same thing with normal numbers, with integers. If I say 42 plus 58, what is the value that we're going to get? Of course, we're going to get 100. But if I have only 2 digits, let's pretend we have only 2 slots, essentially like a mechanical odometer, which is the value that I'm going to get? I'm going to get a 0. So 42 plus 58 is 0 if I don't have another slot. Let's go into algebra, very basic algebra, algebra 101. 42 plus 58 is equal to 0. What does it mean? Well, it means that 58 is equal to minus 42 in our specific case. In the case in which we are dealing with a mechanical odometer and not with normal integers. Wait. So that 58 is not 58 elements. No, it is not. In this case, is the value minus 42. Because 42 plus this symbol, this specific value, is equal to 0. Here we go back to the 1 and 0 of the dolphin. That is not 10 elements. That is 2 elements. It is not 10 ducks. It is 2 ducks. So this 58, it is not what it seems to be in this specific context. It is a symbol that conveys these negative values. I hope this is clear to you, this concept. Now let's jump into our computer, into our RAM. As you can see, I have 2 bytes here that I want to add. I have 1 byte that has all the transistors, all the light lamps turned on. So in my eyes, it seems like a 255, right? I decide to add 1 to this byte. What is going to happen? Well, again, I have the same problem that I have in my car odometer. I don't have the 9th bit where I can put the 1. So this state, this number that in my eyes is 255 plus 1 is equal to 0. Again, algebra 101, 255 plus 1 is equal to 0. What does it mean? Well, it means that this state is not 255, but it is minus 1. To understand this slide, you need only to understand how basic addition of bits works, which is like normal decimal numbers. I will leave you a link in the description to see better how binary addition works, but it is straightforward. And basic equations. Here you have just to move the 1 on the other position and change by the sign. This is elementary algebra. So this particular state in my machine means minus 1. Now I'm going to show you some programs to further understand these concepts. So here I have a program that is able to print in the standard output the bit configuration of all the numbers ranging from 0 to 255. Okay, I won't explain how it works. Maybe you can screenshot it and understand for yourself. Now it is not the point. Okay, otherwise we're going to spend too much time in this topic. Okay, this is the output of my little program that shows all the binary configuration. For example, the number 0 as this binary configuration 00000000. This is 1 byte in memory. Then we go to 1. You see the 1 is the normal 1 representation that you know, of course. -1 has all its bits set to 1. I showed you before. If I sum 1 and -1, I should get 0. Try to sum this configuration and this configuration. What you get? Well, you get 0, exactly. With this specific configuration of numbers, we get subtraction with addition. You just have to add this symbol, this pattern, and you get 0, exactly what you want. 1 plus -1 is equal to 0. This is a trick how our computer performs subtraction through addition. So now what do you see? What we can understand from this program? You see all the positive numbers have this configuration, have all the bits but the first one with a specific pattern. So you have all the ones, of course. We arrive to the last configuration of the positives. As you can see, I have all the bits turned on, but the first one. What is going to happen to this 127, namely this specific pattern, if we add 1? Well, if we add 1 to this pattern, we get 1 plus all the zeros here. What number is that? Here I have -127, which is 1, and all the bits set to 0, and the last one is 1. Which is the value after 127? I have 1 and all the zeros. -127 is 1 with all zeros and the 1 at the bottom. So I think that you understood basically how everything works. So let's check our code from the very beginning. We have 0, which is 0. We have 1, and the opposite is -1, which has all the bits turned on. If I sum these two, I get 0. If I sum these two, I get 0. If I sum these two, I get 0, and so on. So this specific symbol, this specific state, is the opposite of this. How do I go from this to this? Well, I just maybe turn all the bits, like they will become all 1 with a 0, and then I just add 1. If I turn this combination, if I inverse, I get all 1s and a 0 at the bottom. And if I add 1 to this, I get -1. So to convert a number from positive to negative, I have to turn the bit configuration and add 1. This is the concept of choose complement. I leave you a link in the description, of course. So we can notice also that all the negative numbers have a 1 at the forefront, contrary to the positive ones. I finish my sequence with the 127, which is the maximum value representable for a byte, a single byte. As you can see, I filled all the bits but the first one, which is for the negative numbers. Then if I add 1 to this one, I get -128, which is the biggest negative number. So if I add 1 to this, what do I get? An overflow, like an odometer. I jump to the other representation, which is this one. And then from here, I go back toward the 0. To understand the negative numbers, you just have to think about this bit control the most negative integer. In this case, it's -128. Then to understand this other one, you say, okay, I have the minus turned on, so I have -128. What do? I add 1. These are positives. Do you remember? These are the bits for the positive numbers. So it is like saying -128 plus 1. Of course, you get -127. So try to understand, you have to understand very well this passage here. Here we pass from 127 to -128, just adding 1 to this. Okay, this is another program that is gonna print all the bits configurations for 4 bytes. So a normal integer data type. Again, I won't explain how it works, maybe screenshot it. So basically the concept is the same. I have my numbers, my positive numbers here, that this time have much more space. In this case, I have 4 bytes here. As you can see, I have 4, 8, 1 byte here. Then I have 4, 8, another byte, and 4, 8, another byte, and this is the least significant byte. And of course, I have for the number 1, the last bit, which is turned on. To represent the -1, I have the usual 1, 1, 1, 1, 1. This is always true. To have the -1, all the bits are turned on. Why? Well, because if you sum these two, you get 0, and this is exactly what you want. This is a mechanical property of numbers that have a fixed set of numbers, a fixed set of integer, exactly like an odometer. then it's normal. I have all the configuration, as you can see. All the negative numbers have a 1 for front. To get from this to this, you just have to invert all the bits and add 1. Pretty straightforward, okay? At the end, you can see there is a lot of numbers when we're dealing with bigger data type. This one has 4 bytes, so I can reach a very big number. You can see the program is still running, even though our CPUs are tremendously fast, but we have to print a lot of bits, as you can see. So the program keeps going on and on until it will reach its final number. We're gonna stop it and do another program. So this is another program that is gonna print the bits from the maximum number representable in 4 bytes, okay? As usual, screenshot, try to understand it if you want. If not, not important. So I compile it and run. The concept is the same as a single byte. When I arrive to 127 and then I go immediately into minus 128. Here I jump from this configuration, which is the maximum integer. As you can see, I have all the bits, but the bigger one set to 1. So this is the maximum configuration, which is this number in decimal, 2 billion and something. If I add 1 to this number, I get this one that you now understand is the biggest of the negatives, because I have the negative bit turned on and the positive bits, quote unquote positive bits, turned off. So I have minus the biggest negative numbers, which is this one. As you can see, the maximum negative number is exactly like the maximum positive number plus 1, because with the positive, we have to encode also the number 0, the symbol for 0. So we get always a minimum value, which is 1 more than the maximum positive value. Okay, now you have the tools to understand the exercise. You already saw my main function, which has all the numbers, which are minus 42, 0, 42, which are normal integers. Then I have my maximum integer value, that you understood what it is, and the minimum integer value here, okay? Let's try if my code, my algorithm will work. Here I have my function putNumber. So here I declare in the first line a long, which is an integer with 8 bytes. So I can represent much more data with this data type. Then I declare an array that I call C with 10 chars. So this is a data structure of 10 bytes because a char is 1 byte. And then I declare a short E. Then I go copy my number into my long. And if you understood the theory, you already understand what is going on here and why I did this. Then I initialize my I to 0. And I say, if the number is equal to 0. Here I just invert the label and the value, because the reason is that it's very easy to make this kind of error. Assign the value 0 and not the correct one, which is nb is equal to 0. So this is just a trick to avoid this kind of error that is not taken, that is not understood by the compiler. A simple, stupid trick to avoid these tedious bugs that are difficult to find. So I say if nb is equal to 0. What do? I just write 0 and the function is finished. I return. I don't want to know anything else about this. So if the input value is a 0, I just write that motherfucker and I return. On the contrary, if the number long is less than 0, here I use my copy variable, as you can see. What do? I say invert my copy to a positive value, okay? I just multiply the negative number for -1, so you perfectly know that I just convert the number, and I write the minus. So now my variable is an integer long positive that I can process. So now you understand why I need the long and not an integer type. When I make this conversion, if the number is the maximum -1, namely this 2 billion and so forth, when I convert it, what is going to happen? Well, I get an overflow if this variable was an integer, because the maximum value representable by an integer, positive one, is this one, which is 1 less than this one. Do you understand? I'm sure you do. So I very simply invert the number into a bigger data type that can contain, of course, the maximum negative integer converted into the positive. So I don't have any problem of conversion. To be clear, if this one was an int, at this level, I get an error. Or better, I get an overflow. That's basically it, okay? So here I need a long data type. Perfect. So if the number is negative, just convert it. This is what is going on here, and write in the standard output the minus sign. Then I have this while, which we have to spend some time with. I say while my number that I'm sure is a positive one, modulo 10, and that's it for this condition. What am I doing here? Let's check what is going to happen here. I write in my array C, in position E, with a post increment, the number modulo 10 plus 48. My God, how much stuff here. And then I divide my number by 10. Let's try to understand this last point, and then you got the algorithm. While number long modulo 10, what do I mean? I'm sure you already know the operator modulo, which is in a nutshell what is written in this slide. You can conceive the operator modulo like a scissor that is going to cut the number to a specific position and take the value. For example, if I say 1492 modulo 1000, the result is 492. This is an operator that takes the rest of a division. But you can visualize it as a scissor. Very simply, you have 1492 modulo 1000, you get the last three significant values. Modulo 100, you take the last two. Modulo 10, you take the last one. It's like with a scissor, you take the last value. Let's say my number, modulo 10, gives me something. Is there a value? Is there an integer? Because modulo 10 is this operation. For example, 1492 modulo 10 gives me back 2. Okay? So I have a value. I have still something. Now keep this operation in mind. So for example here, if I have the value 1492 modulo 10, I get the 2. And you know that a value different from 0 is the value for truth, right? In C, it is like saying, is this value different from 0? Is 1492 modulo 10, which is 2, different from 0? Yes, of course. But I can use the 2 as a value of truth as well. So I can skip this different 0. What do? I put in position I, that is 0 for the first iteration, the number modulo 10, okay? The number modulo 10, so the last digit. I take the last digit of my number, and then I add 48 to this. For example, 1492 modulo 10, I get the 2, and I add 48. So, as you surely know, I convert this number to a char, and I stock inside the position I, which is 0 at the beginning, and then I go to increase with the postfix increment the value I, so it gets 1 for the following iteration. Okay, so I just stock inside position 0 of my array the char 2, in this case, for 1492. And then what do? I divide the value for 10. What is going on? Division is very similar to the modulo operator. You just have to visualize division as a scissor. So it is going to cut all the numbers that you want. For example, if you divide 1492 for 1000, you cut 492 and you keep the 1, okay? Pay attention here. If I divide 1492 by 10, I cut the last number, okay? So the division is the exact opposite operation of modulo. In modulo, I take the last number. If it was modulo 10, I was taking the 2. With division, I cut the 2 and I keep the 149. This is pretty simple. Let's reread again this while loop. Every time, what do? I take the last number of my digits. And this last number, if it is different from 0, it is gonna, as a side effect, say that this expression is true. For example, in our 1492 modulo 10, the 2 value for truth, because everything different from 0 is truth. Then I stock this last value of my number into the position I as a char, thanks to this plus 48. Then what do? I just cut with my division by one value. So my 1492 is going to become 149. Okay, that's pretty simple. And then the loop goes on and on until this condition is not true anymore. So let's arrive when the number is going to be only 1, because we have cut at every iteration the last digit, thanks to this division. 1 modulo 10 is going to be 1. Okay, so this is true. I put in my array in position I, that now is 3, because it is the last operation. And then I divide my 1 by 10. What is the value of 1 divided by 10? Well, it is 0. In this case, what is 0 modulo 10? It is 0, false. I finished my loop, okay? So this loop is like, take the last value, cut the value. Take the last value, cut the last value. Take the last value, cut the last value. Pretty simple, pretty intelligible, I think, now that you grasp this concept. Okay, so in my array, what do I have at the end of this loop? I have the number stocked in its char form because of this 48 again. I have my I, which is at the last position of my array, thanks to this loop. And then I do another loop. I say, while I is major or equal to 0, because I need also to loop into the position 0 of my array, here I have my buffer that the write function needs, which is, please take the value which is in my array in position I minus 1. This time I have a prefix decrement. So before I decrement I, and then I use its value. So give me, please, the slot in my array in position I minus 1. And here is, of course, the ampersand that is going to give me back the address of this slot. Okay, so every time I have the address, namely a pointer, to the char which is in the last position of my array. In the first iteration, I mean, of course. Then I is going to decrement until it reaches the position 0 in my array, which is my last char that I want to print. Okay, that's a lot of meat for this program, but I think that you understood everything. Let's try to compile and run. Boom. And you see it works. The algorithm is able to print all the values that fit inside an integer. Let's change my long with an integer type this time, okay? And let's check that, and let's try to relaunch my program. You see, I get gibberish here. My program is not able to handle it. And that's because when here I make the conversion, everything breaks up because I don't have enough space in my data type. If here I write, for example, one number less, so if here I write 7 instead of 8, what is going to happen in your opinion? Well, this time it works because this value fits in the positives. You see, this value fits, but the maximum negative value with the final 8 doesn't fit in an integer value. Okay, that's it for this long video, and congrats if you understood everything, okay? There are a lot of concepts here I've tried to make as plain simple as possibly can to me. I hope you appreciate it. Thank you, see you on the next one, bye.